We are now recording. All right. Get this down. Well, I am finishing this up. How was everybody's weekend? Good? You went on a trail? Like hiking or off-roading or? Oh, cool. That's nice. It's gorgeous weather. Holy smokes. Cyan says long. Long in a good way or long in a bad way? Bad. I'm sorry. Cool. Why is this doing this again? I hate technology. There we go. Lots of schoolwork. Hannah said it went really well. Why did it go so well, Hannah? Amber says, I went on a hike Saturday, had way too much training at work. Well, yeah. At this point, I'm just trying to look for the positives in life. So having a job is a good thing at this point. Not saying that spending your entire weekend training is fun, but Ace, you were very productive. Good. Good, good, good. All right. 1 second, Tofeha. And one last thing. All right, road trip to Atlanta. Nice. That's awesome. That is awesome. All right. So let's go ahead and get started. But really quickly, before we do, Wednesday, we are still having class. I'm not canceling class, but this week I'm supposed to be in Chicago for a conference. But obviously COVID decided to put a big old stinky boot in that plan. I have to present for this conference during this class period on Wednesday. So what I'm going to do is just record the lecture offline and upload it to the YouTube so you can watch it then. And I will have it recorded and uploaded before this class period. So you could just, in theory, just watch it during this class period. So it shouldn't be disruptive at all. But I just wanted to give you an indication about that. So don't come and expect me to be here. Jewel said, took my pups to the Greenway. They loved every second of it. Anything that involves happy pups is a good thing in my world. All right, somebody is making a little bit of noise. If you wouldn't mind muting yourself, that would be great. All right, so what did we learn last time? We did learn a t-test. What kind of t-test did we learn about? Okay, so we did have one tail and two tail. But what can you tell me about the type of t-test we learned? Like, what is the known information required for that type of t-test? Yeah, standard deviation, right? Because we need to know about the population, at least some aspect about the population of that mean, and then we're able to actually infer that standard deviation from that sample that we pulled. So yeah, so that's where we start getting into the, we don't have all the knowns of the population. We don't know what the population standard deviation is, but we're going to start inferring from that sample we collected. Yep, you're right, Amber. All right, so what else did we learn?
The R-squared effect size of variance, effect size or percentage of variance.
Yeah, exactly. So R squared. So R squared is a measure of effect size. So Kenya, why would we care about the effect size?
Because we want to see if not only is it significant effect, but the magnitude of the effect.
Exactly. So not only is it, oh, that was a little voice crack. Apparently we've gone back to puberty. So not only is it a significant effect, right, statistically significant, but is it a meaningful effect, right? So I keep going back to this example of cashews because every once in a while you'll see some derivation of this in the news of, you know, those who eat more nuts live longer, right? And what you have to ask is, okay, that may be a statistically significant effect, but is it a meaningful effect? Do I have to eat a pound of cashews to live an extra 15 minutes? Or can I just eat, you know, a cup of cashews every week and live for an extra year on average? All right. Any questions about what we covered last time? For the R-squared? Yeah, absolutely. So the question was, could I go over the interpretation for the R-squared? So the R-squared, again, is telling us what is the percentage of variance that can be explained by some factor, right? And so let's come up with the most basic example. And let's just say this is the average height, right? For everybody in the population. And I'm going to have variability in there, right? I'm going to have a standard deviation. I'm going to have variance, etc. And all R-squared is telling us is what amount of this variance can I explain by something, right? So let's say we wanted to look at your parents' height. So in this case, what percentage of the variance in people's heights can be explained by their parents' height? And so let's say it was an R-squared of 0.2. That means 20% of how tall or how much variance you have and how tall you're going to be can be explained by how tall your parents are. Now, that's an important distinction because what it's not saying is 20% of your height can be explained by your parents. But what it is saying is 20% of the variability in that population or in that sample can be explained by their parents' height. Yeah, so I don't remember what the exact cutoffs are. I think 0.25 is a large cutoff or is a large effect size. I think 0.1 is a medium, and then I don't remember, the standards change a little bit, and then I think like 0.01 is a small or something like that. But yeah, if you're getting 25% of variance explained, that's a massive effect, right? That really helps us predict the world if we can know 25%. Good question. Any other questions? Cool. Here's your fun fact of the day. In 1905, FDR married Eleanor Roosevelt, his fifth cousin once removed. Eleanor didn't have to change her name upon marrying since her maiden name was also Roosevelt. Her father, Elliot, was brother of former President Teddy Roosevelt. How about them apples? Here's another fun fact of the day. I heard on a podcast driving to work this morning. If you were to take every piece of gold that has been mined or has been recovered or panned for or anything like that, since the time of the Egyptians until now, it would all fit in about 3 Olympic swimming pools. I would have thought it would have been a lot higher than that, but apparently that's all the gold we've ever recovered. All right. So today we're going to be talking about t-tests for independent measure designs. An independent measures hypothesis test is going to allow researchers to evaluate the mean difference between two populations from two separate samples. And the important identifying characteristic here is that those samples are independent or sometimes called between subjects, tests. So what do I mean when I say between subjects?
Is that when it's within the same sample or the same group?
Nope, it's the opposite. So it's when you have two different groups, right? So between subjects design would be to say, all right, let's compare all of UAH, or let's compare UAH students and UAB students, right? You can't be both in UAH and UAB. It's between different groups of subjects. A within subjects design, and we'll go over that on Wednesday, is a study wherein every participant gets every level of the design. And so let's say we wanted to see what effect does texting have on your driving. If it's a between subjects design, I would get one group and have them just drive normally, and then I'd get a separate group of a whole different group of participants and have them drive while trying to text. If it were a within subjects design, I would get just one sample and I'd have them drive normally, and then I would have that same group of people try to drive while texting. It would be very unethical. You are absolutely right. Yeah, that's why a lot of those studies have been done in simulators, because you crash, oh well. So what we're talking about today is that first example. The example where you get one group that drives normally and one group that drives while texting. So this just serves to graphically represent what I already talked about. You're pulling from an unknown population. That population has an unknown mean, an unknown standard deviation. You get that sample, and then you have a whole other population from which you're pulling with another unknown mean, unknown standard deviation, and you get that sample. Right? And you can see why this would be beneficial, right? Because now I can measure things that I don't need to know what the entire population mean is, or the entire population standard deviation is. What I'm going to try to do in my driving example is those who are driving normally, I'm going to try to use to infer about the population from which I pulled them. I'm going to say, hopefully this is a representative sample of all drivers everywhere. And hopefully those who are texting while driving are a representative sample of all drivers when they're texting and driving. And that's why things like random assignment and random selection are all really important. So again, we're using this when population means and population standard deviations are all unknown. And because these are unknown, we're going to try to estimate these values because we still need them to run these tests, but we're going to try to estimate them from the sample data we collect. All right, any questions so far? Are all pretty squared away on when we would use this type of test? Cool. All right, so the general purpose of the independent measures t-test is to determine whether the sample mean difference, so the difference between the means of those two groups, indicates a real mean difference between the two populations, or the treatment conditions, or whether the obtained difference is simply the result of a sampling error. Right? So remember, we've talked about the fact that when you sample groups, you're going to get differences in those groups just as a function of sampling. But we want to know whether the difference we see is likely due to that sampling error, or if we could explain it away by saying it's such a low probability event that this would be just due to chance, that it must be due to the treatment. So is the fact that those who were texting while driving were worse at driving, is that due just to chance? Maybe we just sampled some really bad drivers for the texting condition? Or is it in fact the case that that difference is so big, we don't think we can explain it just by chance of that sampling?
So if it was chance, it would be sampling error?
Yes, exactly. And so by performing this hypothesis test, we have a standardized formal procedure for establishing whether that mean difference, the difference between the two groups that I've sampled, is greater than we think would be reasonably explained by sampling error. One second. Mr. Rogers' sweater is a little too toasty for right now. All right. So to prepare the data for analysis, we're going to have to do what we've done already, but now we're going to have to do it for two samples, right? So we're going to have to calculate the mean for the sample, for each sample, calculate the sum of squares, or standard deviation, or variance, right? I mean, you all know how they're all related. If you have calculation of one of them, you can get the others. For each of those two samples. So why am I using S and S squared rather than sigma and sigma squared?
Because it's for samples.
Exactly, because it's for samples, right? I'm not trying to talk about the population, I'm talking about samples. Now I'm going to use the sample information to infer about the population, but these are for samples. Right? So remember, when calculating the variance, do you take the sum of squares divided by n, or sum of squares divided by n minus 1?
N minus 1.
N minus 1, exactly. Perfect. All right, so just as we have done with every test so far, we're going to have 4 different steps. The first one is going to be state the hypothesis. And what is HO? What does that mean? Null hypothesis. Yes, exactly. Yeah, so for the independent measures test, t-test, the null hypothesis says there's no difference between the two population means, provided we're doing a two-tailed test. If we're doing one-tailed, it would be directional. You're then going to go locate the critical region in the back of your book on that same table we used on Wednesday. And what information are you going to need to take to that table when you go look? Yep, so you're going to need the degrees of freedom. Oh, sorry, I didn't mean to cut you off. Whoever just spoke.
You're fine.
What else do we need, Caleb?
I was going to say the number of the sample, which gives you the degree of freedom.
Mm-hmm. Yep, so we need the degrees of freedom. We also need the alpha level, right? And we also need, is it going to be a one or two-tailed test? So if I asked a question of, are UAH students smarter than UAB students, and we're going to test that, is that one or two-tailed? Why two? Well, it is two groups, but this is going to be one-tailed because it's directional, right? So I'm saying, are UAH students smarter than UAB students? I'm not asking, are UAH students different in intelligence from UAB students? That would be a two-tailed because it could be they're smarter or less smart. But in this case, because I'm asking, are UAH students smarter than UAB students, that would be a one-tail. All right, so make sure you familiarize yourself with that because there could be questions on the exam that word it like that. So instead of telling you explicitly one or two-tail, I'm going to ask you to make that inference based off of the way the question is worded. You're then going to compute that test statistic. And I love that this is the shortest sentence despite taking the most amount of time. And then after you do that, you're going to make a decision. So if that t statistic ratio, so the t value you get after calculation, indicates that the obtained difference between the sample means, i.e. what's on the numerator, is substantially different or substantially greater than the difference explained by chance, what you have on the denominator, you're going to reject the null hypothesis and conclude that there is a real mean difference between the two populations or two treatments. All right, so somebody else gives me just an example of a type of research question we would use an independent samples t-test for.
Be for two classrooms, if you got better grades on the test?
Yeah, exactly. So for two separate classrooms, who got better scores on the test? Or let's say I want to compare y'all to my last year's group and try to infer, is this year UAH student better at statistics than last year? All right, and these are the types of tests that they're running. Yeah. Well, it depends on how I ask the question, right? And so if I said, I want to see if this year's students are smarter or better than last year's students, that would be one-tailed. If I said, is there a difference between this year and last year, that would be two-tailed. So these are the type of statistics they're running with any sort of the medical evaluations for treatments for like coronavirus, right? And so one of the most recent approved treatments by the FDA, it's a drug called remdesivir, right? And so when they're doing this test, they're taking two groups who've already contracted coronavirus. One group, they're not giving this drug. the other group, they are giving this drug. And then they'll have some sort of performance metric, right? How long do they have to stay hospitalized? Or potentially, what are their blood oxygen levels at day whatever? Right? So this is the exact type of test you would need if you were performing these types of real-world evaluations. Yes, so one student says there's types of evaluations don't always seem ethical. Yeah, and so it is a big question, right? And so is it ethical to give one group a sort of drug, a treatment drug, and not another group? That's a whole question for ethics. And you start getting into the, okay, well, if we know that this is a potentially effective, would it be irresponsible to not do that? And so one of the things you see now with a lot of the vaccine trials is it's typically the case that for vaccine trials, they'll give half of a group an actual vaccine and then another half potentially just a placebo, and then they just study them over time and see what's the contagion rate over a year. But now they're doing challenge trials, which means I'm going to inject all of my participants with the vaccine, and now I'm going to expose you to coronavirus and see if your system can prevent you from catching it. Right? And so that is where you start getting into some of these ethical questions about, when you get into these medical treatments, is it ethical if you've got a drug that seems to be working to not give it to that control group, right? So that other group you would be testing. And so you can do a whole bunch of other tests based off of probability and stuff like that for these types of medical evaluations. All right. So this is just making a comparison against similar calculations for that single sample t-statistic that we went over on Wednesday and what we're covering today. All right, so whereas with the single sample t-statistic, we were concerned with the mean, today we're concerned about the mean difference, right? What is the difference between mean 1 and mean 2? Where we were concerned about just having the population parameter, here we're trying to infer, okay, what is the population mean as a function of the two different inferred population means? Standard error is the square root of s squared over n, or s over the square root of n. Here, we're doing the exact same thing, except we're just adding a whole other one, right? So you're going to have the square root of what's known as the pooled variance, and we're going to go over the pooled variance in just a little bit, so don't worry about that, over the number of people in sample 1, plus that same pooled variance number over the number of participants in sample 2. And to get that pooled variance, it's going to be the sum of squares of sample 1 plus the sum of squares of sample 2 divided by the degrees of freedom sample 1 plus the degrees of freedom sample 2. Right? Because if you think about it, we're going to have two different groups with two different samples. And the way these tests are run, we need a single estimate of variance. So we're essentially finding the average variance between these two different samples. So suppose we have two different samples from the same population. The first sample has 4 participants and a sum of squares of 36. The second sample has 8 participants and a sum of squares of 56. What would be that pooled variance? We'll calculate that in just a second. But the reason we're even pooling this is because each sample variance provides an estimate of the population variance. Right? And so we're taking the average of those two estimations to try to say, okay, this is probably the better estimate than either of those estimates alone. And with the way it's done, larger samples are given more weight, right? They're seen to be more accurate than smaller samples. Now, why is that? What have we talked about so far this semester that makes that the case?
Is it called the rule of large numbers? Is that what they call it?
Yeah.
Okay.
Yeah, so the law of large numbers says that for the bigger a sample size, the less any individual data point is going to skew that sample. It's the same reasoning behind why small towns in America tend to have both the highest and lowest rates of cancer. Right? Because with a small number of people, having just a couple more people get cancer represents a massive percentage change compared to what a big population is. Yeah, Sunny. Yeah, so the larger, it's the same principle, right? So the larger the number of participants you have, the lower the standard error, but that's as a function of us essentially assigning, and the way we calculate that standard error, assigning more weight to estimates which have bigger sample sizes, right? So the bigger that sample size, the more confident we can be that it's normally distributed and thus has a smaller variance. Yep, you're exactly right. So again, we're going to combine these two sample variances into that single pooled variance such that bigger samples will have more weight on this average. So when I say it's the average of two variances, don't just take those two variances, add them together and divide by 2, right? That's insufficient. What we need to do is take the sample size for 1, add it to the sample size for 2, divide it by the degrees of freedom 1, degrees of freedom 2. So we're finding that pooled average variance. All right, so again, sample sum of squares 1 plus sum of squares 2 divided by degrees of freedom 1 plus degrees of freedom 2. And so if we plug in these numbers from before, with sample A having a sum of squares of 36, sample B having a sum of squares of 56, we add them together. Sample A having an n of 4, so we've got to get our degrees of freedom. N minus 1 gives us 3. Sample B, or sample 2, has an n of 8. 8 minus 1 for the degrees of freedom gives us 7. And so when we plot that all out, that's 92 divided by 10, or a pooled variance of 9.2. Questions about that? Cool. All right, so remember, we still have to get that standard error. And so this is the same equation as you saw on a couple slides ago. So to get that standard error is going to be, and when you see this can be kind of confusing. This square root means that continues all the way over, right? So the whole, it's the square root of the whole thing. So we're going to take that pooled variance divided by the number in group 1, or 4. Then we're going to add that pooled variance again, same pooled variance, 9.2, divided by the number for sample 2, or sample B, which is 8. And once you do the appropriate divisions, so you actually do the 9.2 divided by 4 plus that 9.2 divided by 8, and then square root the whole thing, you'll get that estimated standard error of the mean of 1.86. So this, you'll know, is always representative of these independent samples t-tests. All right, when we used that, that was going to be the one sample t-test. So you know what test you're running. It's a function of the notation. All right, so again, it's the same conceptual thing as what we had for the standard error we used before, except now we just have to average those two different groups. All right, so as a reminder, the equation for sum of squares is going to be that sum of x squared minus that sum of x, square that sum, divided by n. All right, so let's say we had a question that said, I want to know if students are going to wait longer for a tardy professor than a tardy graduate student who's teaching. And the amount of time that students wait is listed below. Test at the 0.05 level in 2 tails. So why don't you go ahead and take a few minutes and try to work this out by hand, and then we will come together and work it out together. All right, take 93 more seconds. All right, so what's the first thing we need to do before anything else? Yes, exactly. Yeah, so we need to establish the hypotheses for this. And now this wording is a little confusing here because I did say, well, students wait longer, which would indicate one tail, but I did say here we're going to test in the two tail. So we're doing it for the two tails. So our hypothesis is that the difference between mean 1 and mean 2 is 0, or you could just say that u1 or mu1 equals mu2. The alternative or research hypothesis is that mu1 minus mu2 doesn't equal 0, or that mu1 does not equal mu2. Was it Mewtwo a Pokemon? No, okay.
Yep.
It was, okay, perfect. I was gonna say it makes me feel old, but then I realized Pokemon's still a thing. So, all right, and we established that we're going to be testing this at an alpha of 0.05. So we need to find out what is our T critical value by looking it up in our table. So if you go to the back of the book, Appendix B, Bravo. And there we go. For the T distribution table, we need to know our degrees of freedom, right? And so to get the degrees of freedom for an independent sample T test, it's degrees of freedom 1 plus degrees of freedom 2. It's not the total minus 1. It's each of those degrees of freedom added together. So we have 14 degrees of freedom. So we go down to the left column to 14. We know we want 0.05 in two tails. So we go down 0.05 into two tails over at 14, and that gives us 2.145. So our T critical value is 2.145 plus or minus. All right, so again, if we draw this curve here, it either needs to be greater than 2.145 or less than negative 2.145. 5 in order to reject the null hypothesis. Yeah, Sonny. Where did I get 6 from? From the data here. So we have 7 participants here, and we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 participants here. And so it's the degrees of freedom for sample 1 and sample 2 added together. So 9 minus 1 gives us 8, 7 minus 1 gives us 6. All right, any other questions so far before we start doing the actual calculations, computations? No, so in this case, N1 would be 9 and N2 would be 7. Yeah, that's all right. Yeah, so it's just the degrees of freedom 1, degrees of freedom 2. So if we go back here, 7 minus 1 for grad students, 9 minus 1 for professor. It doesn't matter as long as it's consistent. Yeah. Yeah, I mean, grad student could be N1, professor could be N1, but as long as you're consistent throughout, you got to make sure the degrees of freedom correspond to the appropriate tests. All right. So now we have fun. Time to play with the numbers. So I went ahead and calculated all of this out, but you all know how to get the mean, right? Just the sum divided by n. You all know how to get the sum of squares, right? So what's the calculation for sum of squares again? Or the equation?
Sigma times x squared minus sigma, this is really messy, I'm sorry.
That's all right.
Sigma x in parentheses squared times n.
Not times n, divided by n.
By n.
Oh, that was like- Yeah.
Yes. Yeah. And so when you use that calculation, you should have gotten 42 point, or 42, let me try that again, 422.88, the sum of squares for the graduate students, and 522.85, the sum of squares for the professor. You've got the n's for both of them, and you have the degrees of freedom for both of them. Everybody with me so far? We will get there in 1 second, Caleb. All right. So now we need to find that pooled variance. Right? So to calculate that pooled variance, we're taking the sum of squares of group 1 plus the sum of squares of group 2 divided by the degrees of freedom of group 1 plus the degrees of freedom of group 2. So we take that 422.88 and add it to the 522.85. And we divide it by that 8 plus 6. And when we do, you get a pooled variance of 67.55. Questions about that so far? So yes, Caleb, you're correct. Awesome. And now we're trucking along. So now we need to get that estimated standard error of the mean, which again, pretend that this is one big square root sign. It's going to be that pooled variance that we just calculated divided by the number of participants in group 1 plus that pooled variance that we just calculated. Again, that pooled variance is going to be the same, divided by the number of participants in group 2. So when we do that, we get the square root of 67.55 divided by 9 plus 67.55 divided by 7. So order of operations, which one do we do first? Parentheses, exactly. So simplify that, and then simplify that. Then what do? And then we add them together. And then what? Then take the square root, exactly. Yes, make sure you feel comfortable with this, because this will definitely be something that trips up some folks on the exam. Even if you've got all the rest of the numbers correctly, make sure you're doing this correctly. Sometimes on these like TI 82, 83 calculators, the order of operations gets a little funky with how they do it. So your best bet is to do the individual steps, unless you're confident that the way you're putting it in gives you that correct order of operations for that. So once we get all of that, we get our estimated standard error of 4.14. And so now we need to calculate that t statistic. All right? So the t statistic is going to be mean 1 minus mean 2 over that sample error, or excuse me, the standard error that we just calculated. There we go. So this should look just like another derivation of everything we've done so far, right? This should look like what we did for the one sample t-test, whereas instead of M2, you have the population mean. You're still using the standard error, but you've calculated it a little different this time. All right, so we're not introducing any new concepts here. We're just using slightly different information based off of what we've been given. And when we do that, we take the mean of group 1 minus the mean of group 2 divided by that standard error, estimated standard error, excuse me. And that gives us a t of 0.95. So we retain the null hypothesis. We fail to reject the null hypothesis. So in this case, that would mean that according to our data, students don't wait any longer for a professor than they do for a graduate student.
Professor?
Yeah.
Someone's asking something in the chat.
Oh, thank you. Appreciate it. Can you go back over the taking the square root of everything? Yes. The square root is just going to be over everything inside, right? And so you're taking the you're taking that pooled variance, dividing it by the number of participants in group 1. You're then taking that pooled variance and putting it over the number for group 2. And then you just take that square root of those two numbers added together. Is that what you were asking about, Dallas?
Yes, I understand. Thank you.
Okay, of course. Kenya says, I think I got negative 0.95, but I think my calculator doesn't always do it. Yes. So that raises a really, really, really good point. When you are doing these types of tests, whether you get positive or negative depends on which group is mean 1 versus mean 2, right? And if I just said you can flip them to be whatever they want, you could get a different t-value in the sense that you could get a positive or a negative depending on just your assignment of those groups. So what you need to do, and this is why I was saying you have to be consistent, what you need to do is make sure that you remember or you've jotted down which group you assign to which for that interpretation. So let me all right. I don't know why it always does this. Okay. So if we've got, I hate, all right, that should be done. Perfect. Okay, so when you have this distribution in here, you have to think about what direction are you interested in, right? And so if it's a two-tailed test, it doesn't really matter what direction. You just have to be able to know which direction you should care about, right? And so if you have, grad students minus the professor, and the professor, people actually waited longer to support your hypothesis that students actually waited long for the professor because this one would have to be larger than this one. That would make the numerator negative, right? And so it would have to be over here for you to interpret that people are actually waiting longer for the professor. However, if we were doing the grad minus professor again, but we thought people were actually going to wait longer for the graduate student than for the ancient old professor, we would expect this to be larger than this one, making that numerator positive, meaning that to support that hypothesis, you would have to be over here. Right? So you have to keep in mind what is the directionality of your hypothesis and what group are you putting where. All right, so make sure that if I ever ask you for a one-tailed test, you prioritize putting or assigning to those groups of mean 1 and mean 2, whatever's going to make the most sense, right? If this were a one-tailed test and I said, are people going to wait longer than, or for professors than graduate students, but I didn't care about the other tail, I just cared about one tail, right? And I thought, okay, well, my T critical is going to be 2.14 here, and I get negative 3.5. Depending on which group comes first, professors or grad students, I could either retain the null or reject the null based off of that, right? So make sure you are prioritizing putting them in the correct direction such that you can make the correct interpretation. Questions about that? Is that a hand? Oh.
I'm still
Awesome.
a little confused. I'm sorry. Can you
No, you're
go
fine.
a little bit more? I don't really know what you mean by what comes first. Like, what do you mean by that? Sorry.
Yeah. No, you're totally fine. So
Okay.
let's come up with a new example, and I wanted to see if UAH students are taller than UAB students. If I put it, let's say that UAH students are on average 72 inches and UAB students are on average 68 inches tall. If I put UAH first, I'm going to get positive 4. If I put UAH second, I get negative 4, right? And so the directionality, it's still the same mean difference, and it's still going to give us the same t-score, except it'll either be positive or negative. So when we have to go and interpret it, we have to make sure that, let's say we wanted to know if UAH students were taller than UAB students, it may make sense to then put UAH students first because we've got a hypothesized direction such that any positive number over that t critical value would be evidence in favor of UAH students being taller than UAB students. Whereas we could still do it the opposite way, but now we know we have to compare it against a negative t critical score. Does that help?
Yes, I understand.
Perfect. Yes.
So in wording your question, you want to answer how you word your question.
So it kind of doesn't matter. I think that's usually the best way of going about it. But like, if the t critical value was plus or minus 2, and you got a -3, I'm not going to take off points if other people are doing it and get +3, so long as your interpretation of those results is correct. Does that make sense? Cool.
Could you draw the answer out on like one of those photos?
Do you want me to draw it up for this? Is that what you're asking? Yeah. All right. So again, if UAH 72, whoa, UAB is 68. If I put UAH first, it's likely going to fall on the right side here. If I put UAB first, your t-score is likely going to fall on the left side. Mm-hmm. All right, so yeah, so just be careful when you're, I don't know why I have to keep remuting it, but just be careful when you are assigning which group is M1 and M2, that you're at least remembering that for when you go to interpret the results. Cool. All right. So as I talked about a couple classes ago, we have certain assumptions when we are running these types of tests, right? One of the assumptions is that the data we're pulling from is normally distributed, right? Because when it's normally distributed, we can make fairly good assumptions about what is the probability that we would have sampled this group, right? Because we know 68% of the population falls between plus and minus 1 standard deviation. One of the assumptions of this test is the assumption of homogeneity of variance. All right, so the prefix homo meaning same. So this assumption is that the variances for these two different samples are fairly close to being the same. They don't have to have exactly equal variances, but they have to be pretty close. And this assumption is necessary to justify pooling those variances and using the pooled variance to calculate that t statistic. Perfect. Yes. And so if that assumption is violated, then we now have two questionable values in our t statistic. The value for the population mean difference comes from that null hypothesis, and the value for the pooled variance. And when we have two things that we don't know, which could explain our result, we can't interpret our data, right? We normally are looking for just that mean difference to explain, but when we've got the additional confound of the variance and the pooled variance, we now can't have any faith in our actual result, right? Because the difference could be to sampling error, it could be to an actual treatment effect, or it could just be a function of violating this assumption. In particular, you can't be certain that rejecting the null hypothesis is the correct thing to do when you obtain an extreme value for t, because part of that could be thrown off by this violation of, excuse me, the assumption of homogeneity of variance. So if those two variances are substantially different, you should use what's known as Hartley's F-max test to determine whether or not that assumption of homogeneity is satisfied. So there are a variety of other tests if you do violate this assumption of homogeneity that you can run. It's not like you have to throw out all your data. But they don't rely on that assumption of similar variances. Now prepare yourself, because the equation for F-max is the hardest one you'll learn all semester. It's just the biggest variance over the smallest variance. I was joking, it's not really that hard, so don't read into it too far. So when you've got those two different groups, you have the variance for one group, you have the variance for the grad students, you have the variance for the faculty data. Whichever one's bigger goes on top. Whichever one is smaller goes on the denominator. So if you ever get an F-max of less than 1, you screwed up. There would never be a reason to get an F-max of less than 1. You would then look it up on the table in the back of your book. In this case, in my book, it's page 652, Appendix B. Table critical values for the F-max statistic. You'll see a series of columns. So the first column farthest to the left is n minus 1. So you find that n minus 1 value for the number of participants. You then, on the top, have the number of samples. So in this case, we only have 2 samples, right? We have the grad students, we have the faculty. Simple. So 2 samples. We go down, we were 9 and 7, I think. So 16, so 15, we'll go down here. We look at 15, and then we've got 2 samples, and you'll see you have 2 different values. Light face one represents 0.05, and the bolded one is 0.01. So just take the 0.05, that'll be the top one for this table. And in this case, we need an F-max score of below 2.86. So this is not like the unit normal table or the t-statistic table where, you know, a more extreme value means essentially something good, right? In the sense that you have been able to reject the null hypothesis. We want something smaller than this value. So I don't know what the actual variances are for that, but you can actually run this test yourself, calculate the variances for each one of those samples, put the biggest one on top, smallest one on the bottom, find that F ratio. And then if it's smaller than 2.86, we're good, we're kosher.
So with that, you wouldn't use the pooled variance, right? You would actually have to go in and
Correct.
calculate. Okay. And then
Yeah, so
you
you're
would,
not, go ahead.
no, I was gonna say, and then you would use the, well, you'd have to pay close attention and make sure you're like following the grid carefully, like with the denominator and numerator. And then you said,
Yeah, so,
and then you said the bold one represents the largest or the numerator, right?
so you're talking about in the back of the book?
I'm talking about the F distribution table, right?
For the F max statistic.
So that's different
not
than
the
the
F
F distribution.
Yes.
Okay. Making sure.
Yeah. So in that case, you should only have one numerator. You don't have to worry about degrees of freedom denominator or numerator. You just have one in value minus 1, and then the number of samples. And so the non-bolded number is for the 0.05, which we'll be using. The bolded would be for the 0.01.
Oh, okay, I get it now.
Yeah.
Okay, I had the wrong table. Sweet. Thank you.
All right, so just as with the single sample t-test, you can compute an estimate of Cohen's d, or you can compute r squared to obtain that measure of the percentage of variance accounted for by the treatment effect. So somebody remind me, what is the equation for r squared?
T squared over T squared plus degree of freedom?
Yep. And so in this case, the degrees of freedom we're using are that same degrees of freedom we were looking at for in the back of the book, right? So you have degrees of freedom for sample 1, you have degrees of freedom for sample 2, you add them together, and that's the degrees of freedom you would be using, right? And so if we have 0.95, oh no, 0.95 squared over 0.95 squared plus, what was our degrees of freedom? 14, thank you. Let's do this real quick. 0.95 times 0.95. All right, that's 0.90. So we would have 0.9 divided by 14.9, which gives us an r squared value for the test we ran earlier today of 0.06. That means 6% of the variance explained in how long somebody stayed in class can be explained by whether they were waiting for a professor or a graduate student. You can also essentially measure this same idea of taking the total sum of squares minus the sum of squares when the treatment effect is removed, divided by that total sum of squares, right? And so that's essentially just giving us the sum of squares for that treatment effect divided by that total sum of squares. So that total sum of squares would be done by grouping all of the data together. So you're calculating the sum of squares now for the graduate students and the professor together. And then you're subtracting the sum of squares for the professor group, or excuse me, well, in this case, it would be Sesame Street watching versus non-Sesame Street watching. And so it would be for that control group, for the non-Sesame Street watching. And that would give you an estimate of the amount of variance explained, the proportion of variance explained. All right. Questions about what we learned today?
When you are looking for, like, let's say this, like, variability explained, like, how would you ask us to find that? Like, will you just say, like, how much, like, what's the difference in variability, or?
Yeah, I would say, give me the variability explained. I'd probably ask you, find the R squared for your test statistic. I mean, I'd be explicit about it.
Okay. Sounds good.
Other questions? Awesome. All right. So again, as a reminder, on Wednesday, I will have recorded a lecture and uploaded onto the YouTubes. We will not be meeting live, so no Zoom, no in-person class, but you will have that lecture still on Wednesday to be prepared for and accounted for. If you have any questions, feel free to send me an email. We can set time to chat. And that's an indication that I've got another meeting to go to. So, adios.
I had another quick question. I can't hear you. Okay. I think
Caleb,
I can hear you
I'm sorry, you started talking before it cut off there.
now. Okay. So like the